Hello and welcome back. We have played around a lot with the Gaussian elimination method, and we noticed that we have to do pivoting sometimes because the pivot is not non-zero, it is actually zero. So we have to use partial pivoting. We also have to use it when the pivot is very small compared to other entries in the same column. So that is also the reason to do partial pivoting. But we noticed that pivot is when pivot is very small and you do partial pivoting, there could be a round of error later. What we notice is that we have to use the partial pivoting with respect to the scales, and this is what is called scaled partial pivoting. So once we are done with that, we are moving ahead from that and we are looking at the interesting decompositions of matrices that we can get using Gaussian elimination method. So let me start sharing my slides and we will right away get into the topic. I hope you can see the slides. It's 40th lecture. We have covered quite a lot. All right, so the Gaussian elimination method is one of the principal tools in solving linear systems of equations. So it's no surprise that it appears in other guises. We now see that the steps used to solve a system of the form Ax equal to b can be used to factor the matrix A. And later, perhaps in the next lecture, we will see that we can use some factorizations and we can solve the system that we have obtained. So it's a both way. It's a give and take kind of system, from factorization to the solution of systems of linear equations, and also from the solutions of linear equations to factorizations. So this factorization is particularly useful when it has the form A equal to L into U, where, as the names suggest, L is lower triangular and U is upper triangular. So of course, not all matrices will have this type of representation. Many do, that occur frequently in the application of numerical techniques. To see which matrices have an LU factorization and to find how it is determined, let's assume to begin with that the Gaussian elimination method can be performed on Ax equal to b without row interchanges. Now here is a secret that I should tell you, that when we are looking at the Gaussian elimination on Ax equal to b, the column matrix B doesn't really have much of a role to play. It's just, it's just a player that comes along. We have to, it's like, for a cricket match, we have to have 11 players. And so if we are short on one player or two, you just pick whoever comes along and you build your team. So if you have to write equation, you have to get a B. But whether you can solve or not really depends on the matrix A. So the matrix A is the main player here. B is someone who just gets tagged along. Okay, so let's start with some such Ax equal to B for any B. Let's not worry ourselves with what the matrix B will be, but it's just some matrix. Okay, and now we assume that this system is one to which we can apply Gaussian elimination without any row interchange. This is equivalent to having non-zero pivot elements aii for each I. So every time you do, so for instance, you apply the elimination of x1 and then there is the remaining part, there the pivot element has to be non-zero. Then you apply that and then the third pivot element has to be non-zero. So at each step, the pivot element has to be non-zero. This is equivalent to having the matrix, having the system Ax equal to B being solved by Gaussian elimination without requiring any row interchange. So we again see that it's just the property of the matrix capital A. B doesn't really come into picture here. Now the first step in the Gaussian elimination method, if you remember, it is about eliminating the variable x1. So for each j from 2 to n, we apply the operations ej minus mj1e1 taking place of ej. So you change your row ej or your equation ej by adding the negative mj1 times e1 to ej. And what is mj1? It is aj1 upon a11. These are the multipliers. Now these operations, they will transform the system into one in which all the entries in the first column below the diagonal, they are all 0 because x1 has been eliminated from your e2 onwards, e2, e3 up to n. x1 has been eliminated. So the first column will be 0. Okay. So this operations, this set of operations that we have performed, they can be viewed in another way. And this operation is simultaneously achieved. There are n-1 operations. Okay, so instead of applying the operations one by one, what you can do is that simply multiply your matrix capital A on the left by this particular matrix. You can check it easily. If you put x1, x2, xn here and then b1, b2, bn, no, you will put the matrix A here. Sorry, you will put the matrix capital A here, and then you see that the first column, which was A11, A21, A31, and so on, is now transformed into A11, 0, 0, 0. So the first column of the matrix A, which is A11, A21, A31, dot, 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 AN1, has now been transformed by taking this product into 1, 0, 0, 0, 0. Okay, if you want to check it for A21, we notice that we will have to multiply by A11 with minus M21 plus A21. That is what we will have to do. Minus M21 is minus of A21 upon A11. So when you multiply M21 with a negative sign by A11, what you get is minus A21. And then this diagonal entry 1 will be multiplied to the second element of the column, which is A21. So minus A21 plus A21 gives you 0. This is what happens every time you are having an ith row, let's say, of the matrix capital M superscript 1. It will have only two non-zero entries. You will have a minus Mi1 in the first column, and in the diagonal you will have 1. All other entries are 0. So when you are multiplying to this matrix, by this matrix on capital A, the ith row here multiplied to the first column will give you the ith row first entry of the product, which is going to be minus Mi1 into A11 plus AI1. But this minus Mi1 into A11 is minus of AI1. When you add that AI1, you are going to get 0. So this is the matrix by which you multiply on the left of the matrix capital A. We are multiplying on the left because we have this equation AX equal to B. And we can multiply to A on the left because left side is free for us to multiply. We cannot multiply on the right to capital A because there is that X variable vector that is sitting there. If you multiply to capital A on the right, you will have to multiply by its inverse to X, and so the variables will also change. Okay, so you can only multiply on the left, and you will also be multiplying on the left of B to have the equality sign. Okay, so this is the first matrix by which we multiply. Now this is a matrix which differs from the identity matrix only in the first column. Let's look at the matrix again. The second row, second column onwards, you just have the identity matrix here. So this is an n by 1 cross n by 1 identity matrix, and below the first diagonal entry in the first column, we have some entries. So it differs from identity matrix only in the first column below the diagonal element, where the entry 0 is replaced by negatives of multipliers. This is all that we have about the matrix capital M superscript 1. So then we have that M1AX, which is equal to M1B, and this gives a new equation, A superscript 2x equal to B superscript 2. So earlier equation AX equal to B can be thought of as A1x equal to B1. Now after multiplied by M1 to A1x, we get A2x, and by multiplying by M1 to B1, we are getting B2. This is what we have. In a similar manner, we continue. We construct the matrix M2, which is obtained by replacing the entries below the diagonal in the second column of the identity matrix by the negative of the multipliers minus M2j, because now we are going to look at the second column. This will change the system by M2. Now we have the system A2x, which is B2. So this will change M2x A2x equal to M2B2, and this will give A3x equal to B3. There is a typo here. This has to be MJ2. It cannot be M2J. M2J will only refer to the second row. We are looking at second column, so 2 has to go to the end. So we have changed the system again. From A1x equal to B1, we went to A2x equal to B2, where the A2 has the property that below the first non-zero entry, the first column has only zeros. Then we got A3x equal to B3, where in the second column below the diagonal entry, we have only zeros. In general, when we have formed AKX equal to BK, we multiply by the matrix MK. This again is the matrix which will differ from the identity matrix only in the kth column. After we have gone ahead, for instance, if you were looking at M2, M2 would have something only below the diagonal of this second column. The first column will remain identity. It will have ones and zeros. We are not making any changes there. So even this matrix MK differs from identity matrix only in the kth column below the diagonal entry, where 0 will be replaced by minus MJK. Here the subscripts are correct, kth column. And then we obtain the next system, which is AK plus 1 x equal to BK plus 1, which is obtained by multiplying to AKX equal to BK by MK on the left hand side. So this process will end when you would have formed ANX equal to BN, where ANX is going to be the upper triangular matrix, the result of the Gaussian elimination method. Okay. And so you will have AN. Remember, we started with A, which is A1. We multiplied to that by M1. Then we multiply by M2 and so on up to Mn minus 1. And so we are only eliminating the variables x1 from E2 onwards, x2 from E3 onwards, and so on up to xn minus 1 from En. The variable xn cannot be eliminated. So we will have only n minus 1 of these matrices. Okay. So this matrix AN is an upper triangular matrix, and we have obtained it by some way. You know, this is the matrix which is obtained by multiplying to A on the left. So this is the U which we will have in our desired decomposition of A equal to L into U. So once you have U and you know what is A, then you can easily compute L, which will be A into U inverse. Right? So the matrix L then has to be L equal to A into U inverse. But we have to know whether it's a lower triangular matrix. Our U is upper triangular, that is all right. Given A, we have the corresponding U using the algorithm given by Gaussian elimination method. And if you multiply to your A by U inverse, now on the right, do you get a lower triangular matrix? Well, it's not very clear. So let's try to obtain this L using the matrices MK that we had formed. So note that each of the MK is lower triangular, because how is MK formed? It changes. You take the identity matrix, look at the kth column, look at the diagonal entry, and below the diagonal entry. The diagonal entry of the identity matrix is 1. Below 1, you are putting some elements. Therefore, it's a lower triangular matrix. Above the diagonal, all the entries are 0. Okay. So MK is lower triangular. It changes from the diagonal matrix, identity matrix, only by changing the kth column below the diagonal. So if you take the determinant of mk, the determinant is 1. The diagonal entries are 1 and there is nothing above the diagonal. So the determinant of mk is the product of diagonal entries, which is 1. So the matrix is invertible. And in fact, the inverse of each mk is also lower triangular. It is given in the similar way. So let's see how it is done. What does the matrix mk do? It affects the row operation ej minus mjk ek instead of ej. This is what it does. So what should be the inverse operation of that? Its inverse operation should reverse this operation. You are subtracting something, the reverse operation should add that same thing. So it should perform ej plus mjk ek instead of ej. And we know that whenever you are looking at any such row operation, what is the matrix we should look at? Now we are going to keep the matrix LK, which is the inverse of MK. That is of the same type. It differs from the identity matrix. It's not just lower triangular, but it is of the same type as MK. That it differs from the identity matrix only in the kth column below the diagonal, where the zeros are replaced by MJK. Here you had, for MK they were minus MJK, here they are plus MJK. This is the only change. Okay. So now the product of these lower triangular matrices is again a lower triangular matrix, because these are all ones on the diagonal and there is nothing above the diagonal. So when you take any two of these, the product is again going to give you something happening below the diagonal but nothing above the diagonal, and therefore we have our desired decomposition, which is A equal to L1 L2 Ln minus 1 into Mn minus 1 Mn minus 2 up to M1 up to A. We know that this is an upper triangular matrix. What we have done is that we have put the inverse of Mn minus 1 here. This Ln minus 1 is the inverse of Mn minus 1. So when you look at this product, the Mn minus 1 and Ln minus 1, they will cancel and you will get identity there. Then your Mn minus 2 and Ln minus 2, they come next to each other, they cancel out, giving you identity, and so on until in the end when you have M1 and L1. They come close to each other and so they cancel out and you get A. This is the proof that the product of these two brackets is equal to the matrix capital A. Okay. So we have obtained a lower triangular matrix into an upper triangular matrix as your A. This lower triangular matrix has the property that all its diagonal entries are 1. So if you have the property that your capital A has the property that Ax equal to B needs no row changes in the Gaussian elimination method, then A has a factorization A equal to L into U as a product of a lower triangular matrix and an upper triangular matrix. So let's do an example. Consider the system 1, 1, 0, 3, 2, 1, minus 1, 1, 3, minus 1, minus 1, 2, and minus 1, 2, 3, minus 1. This is our capital A. Forget about the entries on the right. So we now need to apply to obtain LU decomposition, we have to apply the operations, the row changes. From E2, we will have to remove twice of E1. Okay. From E3, we will have to remove thrice of E1. And to E4, we will have to add E1. These are the things which will give you 0 below the first entry, which is 1. So from E2 we need to remove 2 E1, from E3 we need to remove 3 E1, and to E4 we have to add E1, which is same thing as we need to remove the negative of E1. So this gives our matrix A equal to, we have done, this is our M1 into A. This is the matrix A1. Here I have written it as M1 into A or A2. Sorry, not A1 but A2. And this lower triangular matrix is our matrix L1, which is the inverse of these. We see that instead of -2, we have the second entry as 2. Instead of -3, we have the second entry as 3. And instead of +1, we have the second entry as -1. So here we are just putting MJs, the multipliers, and not the negatives of the multipliers. The negatives of the multipliers are already multiplied to capital A to eliminate the variable x1 from E2, E3, E4. Okay, so the next operations, now we will look at this -1, -1, 5, -4, -1, 7, and 3, 3, 2. So E2 -4 times E1, that's the, sorry, E3 -4 times E2, that's the first operation, and E4 plus 3 times E2, or E4 minus of -3 times E2. So these are the next operations. So they will give us, this is our L1, the matrix L1, which we have not changed at all. This is the matrix L2 here. And this is the M2, M1A. And luckily, it is already a matrix which is an upper triangular matrix. So we see that we have obtained it as L1, L2 into M2, M1A. M2, M1A is this matrix here. L2 is this middle matrix, and L1 is this first matrix. Okay, so L1, L2, the product is lower triangular, M2, M1A is upper triangular. So the resulting matrix M2, M1A is upper triangular, hence U is M2, M1A, and L is L1, L2. Remember that the order is reversed, and therefore we get this decomposition. Instead of capital A as it was, we have written it as a lower triangular matrix into an upper triangular matrix. Does it help us in solving the system? So when we have to solve for AX equal to B, we write it as LUX equal to B, because your capital A is L into U. So we have written AX equal to LUX equal to B. Okay. So we introduce a new variable. We say that we call this ux as y. And therefore we have a new equation now, Ly equal to B. So we solve for y first. So once we have obtained the value of y from here, we will solve for this y equal to ux. So once you get the value of y, we will get the value of u from here. Is it easy to solve? So y will be y1, y2, y3, y4. B is your B, 8, 7, minus 14 and -7. And now L is lower triangular. So it immediately tells you that y1 has to be 8. y1 is 8, which comes right away from the given system, because your L is now lower triangular. Now once you have y1 equal to 8, we look at the second row, which will give 2y1 plus y2 equal to 7. So 16 plus y2 is 7. Therefore, y2 has to be -9. So now y1 is 8, y2 is -9. That will tell you that y3 is 26. And further, these three values, actually only first two, because the last row has a 0 in the third column. So only the first two are enough. It will tell you that y4 is minus of 26. So these are the values for y1, y2, y3, y4, which we write, and now we have to solve for ux equal to y. U is our upper triangular matrix that can be solved by back substitution. Okay, so these are the entries obtained for y: 8, -9, 26, and -26. And then using backward substitution, we see that -13 x4 is -26. So x4 is 2. x3 is 0, x2 is -1, and x1 is equal to 3. So having the decomposition A equal to LU helps us in solving the system. Observe that we had the diagonal entry in the matrix capital L, LII, that was 1 for all I in this method. There are various methods, so the methods will differ by putting conditions on the diagonal element. This decomposition that you get A equal to LU is not unique. what happens is that you can put any diagonal matrix between them and the inverse of the diagonal matrix. So for instance, if you have A equal to LU, then I can write it as L capital K into capital K inverse into U, or let's say capital D, because D is diagonal. So if you have A equal to LU, this is same as A equal to LD D inverse U, where D is diagonal, so its inverse is also diagonal, only the diagonal entries need to be inverted. Now you multiply by D to L and D inverse by D inverse to U. L into D is again lower triangular, because you have only multiplied by diagonal matrix, and the upper triangular matrix is multiplied by diagonal, so the product is again an upper triangular matrix. So the diagonal entries can be changed, and therefore the decomposition is not unique, so we have to put some conditions to get uniqueness. So there are several methods by various conditions. So if you put LII equal to 1, then you get a unique decomposition which agrees with the decomposition obtained by the Gaussian elimination method. Sometimes people say that your UII has to be 1. So instead of taking LII equal to 1, some people demand that UII equal to 1. So there you, after obtaining the lower triangular matrix, you multiply by the diagonal entry to the lower triangular part and by its inverse to the upper triangular part, so that the upper triangular matrix has diagonal entries 1. Yet another demands that LII equal to UII, but this may not always hold. So sometimes some of these decompositions hold and sometimes they don't hold. This last one is very interesting. It is called Cholesky decomposition. It is very useful and we will see it later, maybe in the next lecture, if not in this lecture. All right, so here we had assumed that row interchanges are not needed, and then we obtained the decomposition LU. But what if row interchange is needed? Then how do we work? So if the row interchange is not needed, A can be factored as A equal to LU. But if you are performing a row interchange, suppose EI and EJ are being interchanged. These are the two equations. So ith row and jth row are being interchanged with each other. Then this is achieved again by multiplying on the left by a certain matrix capital B. Every time now, to try and write the matrix A as product of some nice matrices, we try to write all these row interchanges or row operations by multiplying by a matrix on the left. So here this is done by a matrix capital P, which is again a very simple minded matrix. It's not a lower triangular matrix, but it again differs from identity matrix in a very small way. How does it differ? Only in 4 places. You are interchanging EI and EJ. So it changes from identity in the 4 places: ith entry, ijth entry, jith entry, and jjth entry. These are the 4 entries which change. In the identity matrix, all the diagonal entries are 1. So PII and PJJ is also 1 when you are looking at the diagonal entry. But for capital P, these 2 entries are 0, and on the other hand, the other entries are 1. So, meaning to view it pictorially, you view your identity matrix given by an n by n grid, and you have ones on the diagonal and zeros elsewhere. So what you do is that you focus the ith row, jth row, ith column, jth column. So that gives you some nice big square, okay, which is say of size j minus i cross j minus i. There are 4 corners of this square which are given by the ith entry, ijth entry, jjth entry, and jith entry. These are the 4 corners. The identity matrix has ones on one diagonal and zeros on the other diagonal. We just flip them. We say that instead of zeros on this other diagonal, we put ones there, and the usual diagonal of the square, we are putting zeros. So this is what we do. This is the matrix capital P, and that when you multiply on the left to the matrix A, your EI and EJ get interchanged. Such a matrix is called a permutation matrix because it permutes the rows of your matrix. That is what it does. In general, a permutation matrix. So this is the definition. The matrix I gave you, capital P, that is a permutation matrix. But the definition of a permutation matrix is that it's a matrix whose every row and every column has only one non-zero entry. So all the rows and all the columns have n minus 1 entries to be 0. Each row and each column has only one non-zero entry, and that is equal to 1. This is the definition of a permutation matrix. So to give you examples, these are the two permutation matrices of size 2. One, the identity matrix. Identity matrix is a permutation matrix because it is permuting by keeping each row to itself, which is called a trivial permutation. And the second matrix here, it will affect, if you multiply by this matrix to a 2 by 2 matrix, it will change the rows. It will interchange the rows. There will be 6 permutation matrices of size 3. You can take it as a nice exercise to write it down, and in general, for size n, there will be n factorial permutation matrices. Of course, product of two permutation matrices is a permutation matrix. The determinant of a permutation matrix is plus minus 1. So it is invertible. And the inverse of a permutation matrix is again a permutation matrix. So why did I tell you these things? Because we will have to take products of inverses of permutation matrices. If you know the row interchanges that are going to take place, what you may do is that you may already arrange the initial system in the order such that no row change will be needed after that. So if you look at your system and suppose you declare that you will need some row interchange, then you do that row interchange already. So that what happens is that when you are looking at AX equal to B, there is a permutation matrix which is obtained by doing those row interchanges such that PAX equal to PB will not require row interchanges. And if your A was invertible, P is invertible, so P into A is invertible. And therefore, this matrix now PA will have an LU decomposition. So the Gaussian method, elimination method, can be applied to PAX equal to PB. And as a consequence, PA has LU factorization, and therefore A will be written as P inverse LU. You call that P inverse as P prime, but it's a permutation matrix. The PLU decomposition, which is here in the title of the slide, stands for a permutation matrix. It doesn't have to be that particular matrix P. So thus we have written our matrix capital A as a product of a permutation matrix, a lower triangular matrix, and an upper triangular matrix, and most importantly, in that order. We don't have commutativity of matrices, so we should be careful of how we put them in the product. So this is called a PLU decomposition. We don't have time now to do any example about this method, but we will promise to do it in the next lecture. So I will stop at this moment. Already we have gone past our time. So see you in the next lecture. Thank you.